Hello, good morning to all. In this video we continue with the QSPI IP design, and it is a video number 2 for this. Before this there is one video, please refer that for the more details. So let's start with this QSPI IP design. So last video I just mentioned that this flash provide us the XIP system. So I found a nice diagram, so I just put it here for your reference. So the planning for the IP design, the first we need the model of the flash. So for the model of the flash you can refer the websites that I shown here. One is from the Micronics, where you can find the Verilog models. Okay, so whatever your size and requirement, you can download and use that. It's a Verilog model for this QSPI flash memory. Also there is one another Winborn site is there. From there you can also get the Winborn Verilog model for the flash. It is a W250 series, and this is a MX25 series. So depending on the requirement, you can go with this Verilog model. So these are the physical emulation of the chip that is provided by these vendors, Micronics and the Winborn. But if you are using the any flash IP from the specific vendor, so for that you have to get the manuals or data sheet for the same. So mainly we required some command instruction sets, or we can say that command set for that particular IP. So moving back to their discussion. So after downloading that Verilog model, you can see how it looks like. After download, you can get this files from the Winborn and the MX Micronics zip files for the Verilog model. If you see that it is simple Verilog code for the that particular flash chip basically, and the main signals are same, that S clock, chip select, SI, SO, WP and hold. Okay, so these are the timing oriented models for this flash chip. You can refer for more detail from the design download model of this Verilog. So you can also check the Winborn model. Okay, so it is look like I think it is a encrypted model for Verilog. Okay, so but still we can check that and simulate that model as well. Okay, moving back to our discussion. So first we need the model. You can download from the vendor website, and if it is not there, you can refer your IP flash controller vendor for the same. From that manual or the data sheet of that IP or flash memory chip, we have to create the defined command list file. As I told earlier that the data sheet and the IP manuals has some command set or command list or instruction set. Basically there are some related to commands related to the reads, write, erase, like that. On the basis of this command table, we have to create the defined file as define file is similar to this one. Okay, define command read name of the command and the code of that command. It is generated using this command table. Okay, actually I am referring to this MX series 25. So based on that I create the define file. Okay, whatever it may be, you have to just create this define file, because on the basis of this we have to design our RTL code. So after that we have to map each command to its required signal values. So what it look like, this is for the website details from where you can get the Verilog model, and obviously it is a flash memory, so there will be some commands for the read, write, erase, and it is a 8-bit command. Actually the address is a 24. There are some definitions for these, because it is a this kind of flash controller has SPI, dual and quad operation mode. To specify that, we have to generate one signal which define the whether it is regarding to SPI, dual or quad. We have to provide the how many bytes to send, how many bytes to receive, then transmit buffer, receive buffer for the sending the data and receiving the data from the flash. Also we have to provide some start signal so that the mechanism of sending the data and receiving the data is started. So the architecture look like this. So we have two main modules actually, command maps and the command and data transmit receive module actually. So I already defined that the command address, length of transmit, length of receive, and the status data and the send buffer, as well as we have to define the receive buffer as well. Here n is nothing but the size that you want to go with that. It depends on your requirement. For the code purpose I just took that n is equal to 20. So we have to give this these of the signals, and we have to create the some mapping arrangement for this. So how that mapping is done, I can show you. So let's say these are the read related commands, and you can refer the page number 15 for the same from the data sheet. So let's say we go with the first command, that is read. Command code is 03 and can be operated in SPI, and having the address byte 3 bytes, address 1 2 3, and there is no dummy cycle in this, and we can read the data from 1 to infinity. Basically infinity nothing but the almost the length of the buffer, or let's say it is a limit of particular chip, that is 255 or 64, like that. So using that command table we have to create the command underscore list.vh file, that is our define file, where we have to define the command's name and their corresponding values, so that we can have some readability in the code. Okay, for the map purpose we already know we have to give command address, length of transmit, receive, status data. Here n is 20, I took the 20, and we have to include the file command list.vh, so that we can refer the name of the command as in spite of the command value. Okay, so it will generate the count value for the send, receive, and the send buffer. It will arrange the send buffer for the transmission, and it will define whether it is operated in SPI, dual or quad. Also we have to define the dummy, whether that dummy is present or not, and address mode. There is certain commands where the address given by the SPI mode or dual or quad. So we will see how we can provide this address. So how we map this 03H, that is the read data command. We have to place the command send count, that is 4 bytes. 4 byte means first byte is our command, 3 bytes from the address, and if we have some data to further send to the chip, so that number of count we have to given by this length tx. Okay, so if for this read command we don't have any much data to send there, so it will be 0 in our case. We will see that in test bench mode. So for the receive count, we have to provide the how much data you want to read. Let's say 8 byte, 10 byte, 12 byte, like that. So the send buffer is accumulated by this concatenation of this command data address, and the SPI dual quad mode defined by the 0 here. So 0 means SPI, 1 means dual, 2 means quad. So for this command there is no dummy cycle, so dummy equal to 0. The address mode is SPI as well. Okay, so the command look like in waveform is like that. This is command of 8 bit, 24 bit of address, which is also SPI in mode. So the conclusion is that command in 8 bit in SPI, address is in 24, which is sent on the SI pin. There is no dummy, so output comes on the following edge on the SO pin. Okay, so this is a conclusion. So we see the details of this .vh for the define. Okay, it is exact copy of the command table from the data sheet. Whatever the command is there, I just write command underscore and the name of that command and the value of that command. So again we have to check the map file. I just include this command list here, and whatever the required inputs that we already discussed, we have to place here, and it will generate the required signals for the CD TXRX module. Okay, so for sake of simplicity, I just explain you to the detail of this case block with the 03H, which is our read data generation of the signal. Similarly, we have to generate for each command from the table. If you go with the universal IP design for the controller, then you have to map all the commands, but this is not the requirement in ASIC. Basically, there are certain commands we have to choose from. Let's say from this table, all this command is for the read process, but in ASIC we have to use one of the whatever the required for our process. Actually, we don't go for all the read commands in details. So let's say 4 read is good for us, so only 4 read command will be implemented. Okay, so rest of the other read command we avoid to have the optimization process. Okay, so this file will be very large in size due to the incorporation of all the commands that this flash IP has. Okay, so but firstly we have to focus the read side. So I took only the read commands from the tables 030B, BB, 3b, EB, 6b, 7e. So I just create one command defined file, then command map file, which is very simple to understand, and then we have to create one top file on the on this. Okay, but before that we have to elaborate the model file for this flash Verilog flash flash model actually. So we have to create one or number of files which can be have some initial data. Let's say we have to put some data at location 100000. So it will be look like this. So first 01, 02, 03, 1F, 5, 6, 7, 8, like that. So these are the hexadecimal values in a particular file, and we have to give that file as a main file 1, 2, 3. So these are the manual edit we have to do for the loading of the some specific codes in this memory. Also there are some certain changes we have to make. So we have to give the starting address where this data will be stored. So we have to specify the address of that starting and the end of that file. So for 3 files here I provide the location, starting location and end locations. Again there are some certain changes we have to do in this model. There is a VLS value which is around 800k, so I reduced to the 2 for the simulation purpose, because this is a starting time that this model is taking. So for the simulation purpose I reduced it to 2. So again there is a one changes is here. There is some registers, so SR register we can say. I just modified that for the QSPI mode, which is enable. Okay, so also there is a QSPI mode is enable at the beginning. Well, these are the smaller changes we have to do for the simulation purpose. Otherwise this model file is very large in size, so there is no much changes here needed. There are some certain warnings I get, so I just put some comment on that, but there is no need of to make it comment, but to reduce the warnings at the console I just make it comment. Okay, so to overview all the read related commands, I just place the waveform and the conclusion at the bottom. So this is a normal read command, and the command is sent only using the SPI of 8-bit, and then address is sent by 24 bits, and the data come out of SO pin. So summary is that command is SPI 8, then address is 24 based on the SI pin. There is no dummy, so data come out on 8. Then there is a command called fast read. It is the same as to this 03, but the command is 0b. Only the change is that here is a dummy of 8-bit. Okay, so here is the existence of 8-bit dummy. I don't know why it is called as fast, because 03 and 0b looking to be same. In 0b there is only addition of the command, dummy. So there is a next command is 2IO. You can say it is a dual one. Here we sending the command first in SPI, then address is sent on the two pins SIO 0, SIO 1. So in spite of the 24 bits we require only 12 clocks, and we need dummy of 4 clocks, and the data come out on these two pins. Okay, so data required, or data byte required only 4 clocks to get out of that flash. So the next command is dual read. It is the same that of this one, but in spite of the address in dual, only changes it is command is in SPI, address is also in SPI, and the dummy clock is there of 8 clocks, and data come out on this 1 and 0 pins. Okay, so next one is, this is a 4IO read. As it is defined, address is command is on SPI 8-bit, address on 4 clocks, 4 wires, so it requires only 6 clock to send the address of 24 bits. There is a dummy of 8 clocks, and then again we can get the data on the 4 pins. Okay, so within 2 clocks we get the 1 byte. So it's a very looking to very fast. Also there is a chord read mode. So this is looking to be the same one, EB, but the change is that addresses and the dummies based on the SPI. Rest of the thing is same. So there is a W4 read. It is similar to the 4IO read. Okay, the only change is that dummy here is 4 clocks, there is 8 clocks, this one. So moving back to this one, so the summary is that from the all these read commands we got that the command is always in 8-bit SPI, address can be in SPI, maybe dual, again in chord. So the variation is that the address can be SPI, dual, or chord. Dummy can be 0, 8, 4, 8, 4, 8, like that. The data out will be the SPI, dual, then chord, like that. So the summary is this command is always in SPI, address can be SPI, dual, chord. Okay, dummy can be 0, 4, 8, output can be SPI, dual, or chord. Okay, so for this we can have the we should generate the code for the transmit and receive block for this SPI, dual, and chord. So by understanding all these waveforms, we need to design this RTL code for this trans receiver model for this chord, SPI, and dual. So anyway, we in next video we will see how we can generate this code for this this kind of transactions on the flash IP. So anyway, I just have this code as well, but this video already took larger time, so I just keep it these details in next video. Okay, but for sake of simplicity I just show you the top of this. So the top look like this. These are the inputs obviously there will be the clock and reset and start pin. It is exactly what we saw in this architecture actually, this one. Okay, so still for the sake of simplicity I just scroll down for your understanding. This is our command map, this is our trans receiver module, some wires, assignments, and our the flash memory model actually. Okay, in next video we go through all this code in details. On the top of this we can have the test bench as well. I create one test bench for this. Okay, this is instance of the top, generation of the clock, and in the initial beginning I just create one log file where we can store all these details of the command sending and what we received. So the first command is this is a reset process. I kept the everything is 0. Then after some clocks I just put some message on the log file and provide the command for the read, then address. Okay, then there is no data to send. Okay, so but we have to read the 8 bytes from the flash. There is no status values, so I just kept it as 0, and we provide the clock for this start. And after some time busy goes and it will return as 1. So after the busy release I just read the what we received one by one bytes. Okay, and put it in this log file. So I just simulate this and we can have that file as well. Just compile. Initialize simulation. Actually what happened, this kind of thing is very wide in spectrum to explain and get the thing done. So might be required more time to explain all these details. So I think we required some more time for this. I put all the required signal here. In next video we will see all these details, but just for the read side simulation I just explaining the things. So we also go through all the signaling, but for now I just create one log file from where you can see what happened right now. This is a log which is created. From this log file we can see the details. The command is 03, which is read command. The data 8 bytes of data is we are getting 01, 02, 03, 1F from the location 100000. Okay, this is the location where this data is stored. Also the second command is fast read, also we get the same data. Then again there is a to read command bb and we get the same data. We are keeping the addresses same. This is a dual read 3b, we also get the same data, and there is a 6b, we also get the same data. For all the read commands we are getting the same data. You can check also the data from this file. This is location, these are the 8 locations we are reading, and we are keeping this location at the as we already told that it is starting from the 10000. Okay, so the main one file is our this one, and we are having the data in that file, this one. So from this log file it is very much clear that the whatever we are trying to read from this location, it is a correct value we are receiving from the all the read commands. Okay, in next video we will see all the details of this commands codes or modules, but for sake of simplicity I am just showing that it is working well for this read process. Again, there is a much to discuss, like in the as we saw in the plan, we have to check this device related code. Okay, then last we have to use the write code. Okay, so these are the little bit complicated process, but stay with me. I will explain these things in coming videos. So anyway, thank you. Okay, thank you, bye.